Yeah, no, I didn't even know like Aura. And then I'm going over here. He told me something this way. He was like, yo, last night I got signed up for CPD. My mom.
You made notes explaining that. When you find your extremis, do you need to find the whole point? Like,
No, I prefer you to just give me the Y value. Got it. Okay. The full order pair.
yeah.
Depends on the direction.
Okay.
Sometimes it will just say X value, sometimes it'll say the full order pair, so just do whatever it's like.
Okay. And then one more question. I think there's something that reading somewhere, but like, whenever a critical point
Lands at the end point, it's not in the interval.
Okay.
Move it.
Okay. Is that good? Like, there's the parentheses on
It has yes, that's right. So, they can't guarantee point because in fact, you can only guarantee a differential between the endpoints. So you can't guarantee that last end.
Thank you.
Thanks.
We don't know.
As I was running in from my car, I left my notebook in my car, which has my stuff in it. I can show it to you during like after this class.
Okay, thanks.
No, okay, let's go. I'm ever into any school. I'm in school. Oh, just about my way.
Okay, let me go over the calendar for this week. So, I'm going to finish up on second derivative test, just a few more things about that. But today we're going to focus on sketching a curve, and basically we're just going to take the data that we got from the first derivative test, the test for concavity, and then putting it all together and seeing how all that can create the shape of our graph. So I don't think this is going to be too challenging, but the derivative graphs is what's more challenging. So if we have time, I would like to get started with that today, and then tomorrow we can also spend a whole class period on that. Optimization. I consider this more of like a minor topic, but it does have kind of like a word problem feel to it. But we'll just focus on a couple of types of problems, and then we'll move on to our quiz review. So I'm hoping we can start quiz review on Thursday. Then we have Thursday, Friday, and Monday to do quiz review. And then next Tuesday will be our quiz, and it'll just be, a quiz unit over these topics here. Okay. All right, so if you can turn to page 35. All right, so it says sketch the graph of the function and find the below information. So we're going to find as much of this information. Some of this does not apply because the fact that our graph may not have a vertical or horizontal asymptote. So, but we're going to try to fill in as much as we can. X-intercepts and y-intercepts, this comes from the original function. So first step, x-intercept is where we set y equal to 0 and solve for x. So then we're going to set that equal to 0. Okay, so we're going to go ahead and factor out the GCF. Okay, so I have three critical points here, 0 or plus or minus √5/3. These just kind of give us an idea that we have three x-intercepts, and we don't have to be exact, but we just know that these are going to be some decimal values a little bit past 1. So maybe positive 1.1 and or up close to, probably closer to 2, like 1.3, 1.4. And then y-intercept. Y-intercept means that you're just going to replace all the x's with 0. So the x-intercept and y-intercept are both involving 0. So I think this ends up being like 1.8, 1.7. So I'm just going to just ballpark value of where those x-intercepts will be. There's no vertical asymptote or horizontal asymptote since we're not dealing with any variables in the denominator. So we know it's going to be a polynomial. It's going to be a nice smooth curve. Next up, let's go through our first derivative test. So we'll set f prime equal to 0, find our critical points. And now these are going to be places where slope 0 is, and also where our graph will be increasing and decreasing. So let's pull that from f prime. So we go through power rule. Setting f prime equal to 0. Continue factoring. Three critical points, 0, -1, and 1. So we can place all of them onto our slope sine line. And then we're just testing our intervals here. So I'll test -2, I'll test -1/2, 1/2, 2. So -2 into f prime. So x squared is always positive, so I'm going to ignore that. So that negative is going to carry over. Negative, negative, so 3 negatives makes negative. And with your slope sine line, use arrows with the positive or negative slope to help indicate how the graph is going to be moving. This is going to be a downward movement. Plug -1/2 in. I get positive times negative times negative. So 2 negatives makes positive. Right? Plug 1/2 in. Positive, negative, negative, 2 negatives still makes positive. and then plug 2 in. Positive, positive, negative. So 1 negative. So from our slope sign line, we can have a pretty good idea how the graph is going to look. What would you expect at -1? Yeah, relative min. Is there anything at 0? No. So the graph is going to flatten out for a moment, but then it's going to continue rising. So neither a max nor min, but there is a slope 0 at 0. And then at 1, there's a relative what? Relative max. And if I want to find the locations of these order pairs, I would have to insert these x values back where? Yeah, into the original. Okay. So let's just practice writing out our because statements, since that's going to be a important step for what we need to do on our quiz. So let's say this, relative minimum at, and if I plug -1 into the original function, I'm going to get 5, see, -5 plus 3, which is -2. And then I want us to practice writing out the because statements, because there are because statements for relative extrema as well. And the reasoning is because f prime changes from negative to positive. Next up, relative maximum at, so plug 1 in to the original function. This time I'll get 5 minus 3, which is 2, because f prime changes from positive to negative. We can also indicate our increase and decrease statements. So we have 2 intervals of decrease. So we have 2 intervals of increase. Oh, and by the way, we're removing, or if you want to remind yourself that we're not going to involve any of these test points. So the -2, -1/2, 1/2, 2 should not show up in any of your interval statements. Oops, sorry, increasing. Let me. Again, students have asked, wait, can I just merge the intervals together? In this case, you can. You could merge it together, but I would say it's just safer to just always keep them in separate intervals, because if you have them in separate intervals, you're never going to get points taken off when it could have been combined. So I just feel like that just takes one less decision out of what you need to do, and that way you don't have to worry about ever having to combine if you just do everything separate. All right, decreasing. Okay, so our function is decreasing in this interval and this interval, -infinity to -1, and then from 1 to infinity, because f prime is less than 0. Now, I just want to show you that just from this alone, we should be able to sketch the graph, but our graph just won't be as detailed as it could be. So I find that it's easier if we just do a rough sketch of this, but then not commit to the full shape of the graph until a little bit later, okay? But I think it's always a good, I like the habit of doing two versions of the graph, one graph based off of the slope, and then the second graph to kind of go back and retrace it with more detailed curvature. So from this alone, I think we should be able to get a pretty good picture of the graph because we know that there is a relative min at -1, -2. So I'm just going to have my graph go up to 2 and -2. So I'm going to plot these points here, -1, -2, +1, 2. And I'm just going to do a dotted line because I don't want to commit to the full curvature of the graph. I just want to kind of have a basic path laid out. So I know my graph is decreasing till -1. And I know that all these points is going to have to go through all these points, right? Because these are anchor points from our X and Y intercepts. And then we have max and mins. So we're going to just do this. We know up to -1, our graph is going to be decreasing. Okay. After -1, our graph is going to be rising. It's going to hit a slope 0, so it's going to flatten out at 0. And then it's going to continue rising, hit a max at 1, and then continue decreasing. Okay. The reason that I'm doing dotted line here is because we don't have any information about the concavity of the graph, even though we can probably guess what the concavity is. But it's nice just to have something laid out so that when we get to our second derivative sign line, we just have to go back and retrace it, and then we can just give it a bit more emphasis on how the graph is curving in terms of is it concave up or concave down. All right. But at least we have the rough path of the graph. Okay. All right, so now let's move on to our second derivative sign line. So let's find f double prime. So we left off at f prime. So let's just go through power rule again to get to second derivative. I'm sorry, -60. Power rule, bring down the 4. Set equal to 0. Take out your GCF. Okay, we can set both parts equal to 0. -30x equal to 0, which is x equals 0. So plus or minus root 1/2 is just plus or minus root 2/2. I find that to be more recognizable. That's just going to be like around 0.7. Or -0.7. So I'm just going to place them onto my second derivative sign line. And now these are no longer potential max and mins. These are now going to be potential points of inflection. And now anything we find are going to give us concavity. It's not going to give us max and mins. So we're getting a different set of information from this graph, but it's still going to be something that we can translate onto this graph. So I'm going to use test points. So this is around -0.7. So, and also you get to use your calculator as well on the quiz. I'll choose -1. I'll choose -1/2 here. I'll choose 1/2, and I'll choose 1. Because 0.7 is greater than 1/2, so I can place that 1/2 between 0 and 0.7. Okay, so I can put it into my second derivative. -1. So that's going to give me negative times positive, which is positive. So I know that my second derivative, positive, is not increasing slope. It's talking about concavity. So it's going to have, the graph is going to resemble portions of a parabola opening up. Next up, I'll test -1/2. -1/2, so negative times negative. Now, -1/2 here is going to force that to be like 1/2. 2/4 is 1/2. So 1/2 minus 1 is negative. So 3 negatives makes negative. 1/2, negative times negative. So 2 negatives makes positive. Plug 1 in, negative, positive, positive. So 1 negative makes negative. If I want to find, let's see, these are all points of inflections because the signs change at each of these critical points. But if I want to find the ordered pair, I'll have to insert them back into the original function. It's going to be a little messy. So I think for now, for sketching purposes, as long as we know that our points of inflection is going to lie along the path of the graph, we can kind of estimate where they're going to be. So -√2/2. That's going to be like -0.7. So that's going to be somewhere here. So I'm just going to highlight where my estimated point of inflection is going to be. It's not that important that we nail down the exact y value, but we just know that point of inflection it's going to land somewhere along the path of the graph. So that's another reason that I like to sketch the graph after f prime, because you're not having to create a new path. You just have to kind of work along the path and just update the information. There is a point of inflection at 0 as well, and we do have a 0, 0, so we know the point of inflection is going to land there. And then √2/2, that's 0.7, so 0.7 is somewhere here. I'm just going to kind of estimate. It's not that important where the y value is, as long as you have an idea where it is along the graph. It's going to be somewhere at 0.7, so I'm just going to highlight that point. Now, the nice thing about having all these point inflection highlighted is that we can just kind of go through and sketch the graph with the appropriate curvature and just connect from dot to dot. So I want initially my graph to show concave up. So up until my first red dot there, I'm just going to have my graph kind of have a visible U shape to it. So I'm just going to kind of over exaggerate so that I can get that concave up to show. And then from this point to this point, my graph is going to switch over to what? Concave down. So now I want to connect these 2 points to kind of have a visible parabola opening down feel to it. So I'm going to kind of give it that concave down shape. Now, notice that I can't do a full concave down parabola because the point ends here. But this is still giving that concave down shape as we move. Next up, from 0, 0 to the next point of inflection, my graph is going to switch to concave up. So I'm going to give it a U shape there. Concave up. And then finally, the last remaining portion, concave down. So the remainder of the graph, I'm just going to give it that upside down view. Sorry, guys, I'll get that.
You actually hear a funny book.
Okay. Okay, so we can just write down the few statements that we need for concavity. So we can have intervals of concave up, intervals of concave down, and then points of inflection. And then these all have because statements that's associated with them. So I'll go ahead and spend a minute just to write these statements down. So concave up, the first and third interval, because f double prime is greater than 0. Concave down in the second and fourth interval, because f double prime is less than 0. And the point of inflection, this case, we don't have to worry about the y values, just specify the x values, and the reasoning is because f double prime changes signs. Okay, so I want us to practice writing out these because statements because I'm going to be asking you to justify your intervals on your quiz as well.
For point of inflection, should we find like full point?
I just want you to know how to find the y value if the problem asks you for it, but I think on the quiz, I'm just going to have you just give me the x value. But if you want to find the ordered pair, it's going to have to go back to the original function. Okay, should we go? Okay, I'd like to do a little bit of preview into a derivative graph. There's still another function that I want us to do a full curve sketching with, but maybe I can save page 36 for tomorrow. I just find that that I would like to have more, just have additional days just to kind of have the derivative graph sink in a little bit. So if we can turn to page 40. Okay. So I think something that is going to get take some time to get used to is if we had a function graph in front of us, it's easy to interpret because we know, okay, that's the max, that's the min, that's the max. We have increase, we have decrease, increase, decrease. But what if this graph was not the original graph? What if this was the derivative graph and you're asked to figure out what the original graph looks like? So that's something that AP exams, they love doing this. They love giving you the derivative graph and then asking you information about the function graph. So let's just start off. Let's just treat this like the original graph. This is the original graph. We're going to gather information so that we can create the derivative graph, and then we'll talk about the second derivative graph as well. Okay. So let's just create a slope sine line just based off of what we see in front of us. So slope sine line, let's just find slope zeros. I know this isn't I meant to have all this lined up at integer values, so it doesn't quite line up perfectly, but where do you see slope zeros on this graph? What x values? Where do you see it? Slope zeros. Negative. Okay. -3. -1. And where else? 1. Okay. So let's just place them onto our slope sign line. -3, -1, 1. Okay. What we see is what we interpret, right? This is the original function graph, so everything is going to be straightforward. Where do you see from -3 from -3 to -3? What do you see here? What slope do you see? Positive. Okay. So we'll do positive, and it's going to keep alternating, right? So positive, negative, positive, negative. All right. Now, let's say we want to take all this and put it into a graph that's where the y-axis is now redefined. So right now, the y-axis is defined as these are just the y values, right, of the graph. Right. Now, what if we no longer want to represent the y values of the graph? What if now we want the y-axis to represent the slope values of f of x? If that's the case, then this graph is now going to be called the f prime graph. Okay. So this is now a derivative or a slope graph. So now all the y values, they don't represent the position of the graph anymore. Now the y values represent, sorry, the y-axis represents the slope values. So that means anything above the x-axis are all variations of positive slope. I'm going to draw an arrow pointing up to indicate where that's going to live. Anything on the x-axis is what? Slope. On the x-axis, zero slopes. Okay, so all the zero slopes will land here. And anything below the x-axis is where we want our negative slopes to look. So because our y-axis now represents the slope and not the position, it's going to look a lot different than what our graph is. Okay, so first is your slope zeros are going to land, these are now going to land on the x-axis, right? Because at -3, there's a slope 0. At -1, there's slope 0. At 1, there's slope 0. So now these are now going to land at x-intercepts on your f prime graph. Okay. Up until -3, what do you see here? These are all, okay, increasing. And also the slopes are all what? Positive. So again, this is not exact, but just to kind of give a ballpark value, what's happening to these slope values? I know these are all positive, but what's happening to these slope values as we head towards -3? All right, so maybe it's like a 4, then 3, then 2, then 1, right? You see how these slope values are decreasing? And that's what's going to happen here. The graph is going to do this, right? Imagine this is a y value of 4, then 3, then 2, then 1. And that's because it's describing the slope values as it moves towards -3. Now, between -3 and -1, these are all going to be what? Negative slopes, right? So negative slopes means my graph is going to have to live in this region. So, and you have all these points already kind of helping you anchor your graph. So you know your graph is going to loop down and then come back up. Right? It doesn't really matter how far you loop down. You're just trying to make your graph as smooth as possible. And then from -1 to 1, what do you see here? Positive slope, so it needs to live above the x-axis. So it's going to have to come up and go back down. And then to the right of 1, these are all negative slopes. So they're going to just go down like this. I think some students have a little bit of trouble is, wait, how do we know that it's going to loop back up besides the fact that these points are here? So if we look at, again, these are ballpark values. These are not going to be exact, but you can kind of imagine a slope may become -1, -2, -3, but then at some point it's going to kind of move towards back to 0, right? So -3, -2, -1, 0. So the pattern of -1, -2, -3, -2, -1. So you can see that as the slope gets steeper, it's going to have to come back down to 0. So that's what's causing that y value, that slope value, to come back up to 0. Okay, next up, let's look at a second derivative graph. So second derivative graph is where we are now plotting the concavity of the original graph. So let's say I gave this information to us that there's a point of inflection at x equals -2 and x equals 0. So -2 and 0. This is where the concavity changes. So concave down to concave up to concave down. Okay. So your second derivative sine line, you're going to put your point of inflection onto your graph. And now we're going to base this off of the original graph. So original graph here, this is what? Concave down. So I'm going to indicate concave down on my slope sine line. I'm sorry, concavity sine line. From -2 to 0, my graph switches back to concave up. And then back to concave down. Okay. So here's my second derivative sine line, second derivative graph. Again, because we're at the second derivative graph, the y-axis is continually changing. It's now representing something else. So now we want the y value to the y-axis to represent the concavity of the original graph. So anything above the x-axis is going to be where concave up is going to live. Anything below the x-axis is where concave down is going to live. Anything on the x-axis is where your point of inflection is going to live. So now our point of inflection, -2, 0, is going to land on the x-axis. So -2 and 0. All right. Concave down, where do we want our graph to live initially? Above or below the x-axis? Below, because that's where we want the graph to be. So the graph is just going to rise up to that anchor point there. Between -2 and 0, where do we want our graph to live? Above, so it's going to be above. Now, this is a little bit confusing because students see this U and then they feel like they have to match that with a U shape, but the graph is going to end up looking coming back down because it has to loop back down. So I think some students get thrown off. They'd say, oh wait, this looks like concave down, but I'm supposed to be concave up. This concave up shape is meant to describe the original graph. It's not meant to describe the shape of the second derivative. All right. To the right of 0, where do we want our graph to live? Below. So it's going to end up looking like a parabola opening down. I want to draw another connection with something that we already know. What degree does this look like to you? What degree polynomial here? If it has 3 changes. So this is like maybe in the family of -x to the 4th. All right. All right. What's the derivative of -x to the 4th? So y prime is equal to -4x cubed. So if you look, this is in the family of -4x cubed, right? This is a cubic function. All right, what's the derivative of -4x to the 3rd? So I want you to see that power rule wise, we know the derivative, but then graph wise, it is also matching up, right? This is a cubic function. And then find the derivative again, -12x squared, that's a parabola. And we see that graph show up as well. So graphically, and algebraically, we see the derivatives matching up. Okay, one more thing that I want to show you before we can try another example is the fact that whenever my graph has a negative slope on the f prime graph, that is indicating to us where our graph is indicating concave down. So whenever the slope is negative is where our graph is showing concave down. So negative slope on the f prime, because my slope is becoming more negative, that is what's going to indicate concave down. And then anything that is positive slope on the f prime graph is going to be concave up. Anything that is negative slope on the f prime graph is going to be concave down. And then look to see your point of inflection too. Your point of inflection you can also find from the f prime graph, because the peaks and valleys of your f prime graph will be your point of inflection, right? Because the steepest parts of the graph is going to be showing up as points of inflection. So everything is connected. This is the most important starting point. So we need to be able to start at the f prime graph and be able to gather information about the slope and the concavity. That's what we're going to be practicing mostly for the next day or two. Okay, let me just start us off here. So page 41. If we can get the slope and concavity sign line up and running, then everything is going to be a lot easier. And that's what I want us to be able to do. So what we need to be able to do is be able to look at an f prime graph and be able to gather information about the original graph and the concavity graph. So f prime graph, what I like to do is whenever you see an f prime graph in front of you, go ahead and start labeling what you're looking at, because the y-axis is now defined differently. So I like to do this. Anything above the x-axis is indicating positive slope. Anything below the x-axis is negative slope. Anything on the x-axis is slope 0. So let's create a slope sign line so that we can get a picture of the movement of the original graph. Okay. What can we place onto our slope sign line? What are our critical points? We're going to be targeting slope 0 to begin with. So what x values do you see? -4, 2, and 1. Okay. So -4, -2, and 1. Okay. Now, don't look at the rise and fall of the graph. Look at the location. Okay. So to the left of -4, where's the graph located? Above or below the x-axis? Below. So I know the graph is rising, but this is located below. So we want to indicate that as what? Negative slope. Okay. So that's negative slope. Between -4 and -2, don't look at the movement of the graph. Look at the location. Where is this located? Above. So positive slope. So between -2 and 1, below, negative. To the right of 1, below as well. So still negative. Okay. This is the most important part. If you can get to this point, the graph will get a lot easier, because you're just going to make your graph rise and fall based off of what the arrows are telling you. All right, let's do one more thing here. Let's create our second derivative sign line. Now create your second derivative sign line. Now you're gathering point of inflection and concavity. Now your point of inflection is going to come from the peaks and valleys. Okay? So wherever the max and mins are of the f prime graph is where the point of inflection is going to live on the original graph. Because point of inflection is where your steepest parts of the graph is. And then this is the steepest part, because that's the highest slope value. That's the most negative slope value. So we're going to say -3, -1, and 1. Now, instead of looking, now we can look at the rise and fall of the graph. Right? Because f double prime is describing the slope of f prime. So a positive slope is going to indicate what? Concave up. A negative slope is going to indicate concave down. Positive slope and negative slope. The hardest part of this is trying to get these two sign lines to be up and running. Once the sign lines are up, then we can ignore the graph and then just sketch the graph based off of what we see on our sign line. Okay, so we'll practice that tomorrow. This is our focus for tomorrow. For today, homework, you guys will just do a full curve sketching problem, just page 36. You'll just do this problem here. I'll send out a reminder and you guys can also check your key. You can also graph this in your calculator to kind of get a visual as to what you're moving towards. Okay, so page 36 will be your homework. Have a great day, guys.
What?
Used to each other doing like they were just like if I had to wait. Yeah, just speak up. What was the day party?
Thank you. Appreciate it. Have a good day. Thanks, you. All right, thanks.
It's like name the test. The tag, yeah. That's all I have. Name the last, just gotta name those more than name the last. That's my point, bro. Just gotta do something like that. It's like name four tests besides.
Thank you. See you every day. Bye now. Bye.
Did we get to see requests soon or?
I'm halfway there, so hopefully Thursday.
Thank you.
Thank you.
Thank you, Shane.
Have a good day.
You're like, actually, major. Yeah, like, actually.
Oh, yeah. What kind of? Oh, sorry. Your card, you got it. Yeah.
Then he got out.
Thank you so much.
I've been ready since 8:40. 7:40. Oh my God, you know what I mean? I think I don't expect this thing. Okay.
Maybe it's just more than yeah.
I just. It's like.
Page 30 and those 20.
Or 20.
Okay.
Do you have a charger?
Okay, sure.
Thank you.
I didn't know it was Saturday. I think, you know, she would have come in like near me there.
Like, I find like explaining.
Well, tell her,
Oh, yeah.
why don't you just start from his house at like 7:30? Make time for him to do.
I don't like
Usually it's really. I don't have my phone. I still like me when I'm here.
Thank you.
Strong fire.
I leave my house past 7:40. I leave. Usually my renting house gets 7:50, but I have to pick up. I can't leave my house. I don't do this. I just feel the two benefits. I don't want to go to the. So, yeah.
Very tall, it's right. Like. Can we add your calculator? That's my grandma's better, so it's all done it yet. Okay, did you click for the keyboard? Do the evaluation stuff?
Yeah.
Probably. Okay.
Yeah.
Yeah, so we just. And looked at it, I was at 4 and like. Dude, like, it's like. I don't even know positive or negative, like, I was maybe, it's like, probably. Right. Like, if you created it. They're looking at it and I'm like. If it was Miller, for instance, like, maybe it was something that's fucking nice, that's class, you put it in that class, no. I guess that comes in handy, or the for class, oh, tell you guys to say the class, or no.
Your math.
I guess that's the only positive.
What? My.
This is why. Oh, yeah, I can't.
I did my I know.
What'd you have, please?
Oh, no, this one. That's right. I'm so happy. It's so like, yeah. One Friday, they're not blindfolded thing, and they're like moving us. And I was like, I don't think you're on. London was right next to it.
No, it's only 2.5.
And then the boyfriend, it's like.
Out of town the entire.
I'm glad you don't. And you just talking on there, right?
I'm gonna say like, I was curious and I wanted to go.
That's good.
And, my friend has a. So I got tripped, you know, so you were- you were- And then we see them. No, it's that one trips in the one, the yellow. Isn't that gonna be coded?
That's all.
Interesting.
That sounds
You call
like.
dedication.
Right.
And I'm gonna bring some bananas.
No, I don't think anyone put it on.
I think she wants bananas.
All right, let me check, you guys have page 20.
Three times two, 5.
Are you excited for our essay? No, I know, I don't feel bad. I don't care enough. It's like so annoying, like, this is my last one. So like, yeah, it's okay. Okay, what's your other one? What's your highest score? Oh, that's good. I mean, it's so good, looks like it's fine. I'm so kidding.
Yeah.
Well, just from. I like how, like, I don't forget it.
Yeah, I'm gonna pull out. I'm gonna explain in the wall.
My goal is the 1,300. I was like the 12. Yeah, it's like one session is 100. For this one, I'm hoping for a 1,200. Yeah, but like that. I didn't study.
Yeah.
I'll accept it.
Halfway there. I got like an 11. And my sister person. But.
Thank you.
I forgot how to do algebra.
Mr. Yang, how's fancy?
Got my first win.
Hey. I know you had the Eagles.
Getting together, Vikings defense.
I did. That's what helped.
What you do?
I did.
Whoever had.
That's the only reason I won.
It's so good.
I don't know how you called that.
They scored like 30 points.
Oh.
Who did?
Hey, did we get 5 points from the quiz now?
Okay. let's go to, page 11. So page 11, we're gonna do, this is, I know this looks intimidating here, but we're really, this problem is going to kind of walk us through the process. So we're just having to focus on the cone to begin with. And then once we get that out of the way, we can worry about the cylinder later. But give me a second here. Let me set up and then we'll walk through this together. But pretty much what you guys did with your classwork and homework is basically what part A and B will feel like. So, but just give me one moment here. Oh, God, thank you. Thank you. All right.